Hello again, and welcome to our third lecture in the series Aerodynamics for Pilots, this time a lecture on aircraft performance. In this lecture we'll be putting together what we've learnt in the lectures on lift and drag, together with some power plant characteristics, to produce the performance characteristics of some real aircraft. Let's start with what lift and what drag and power mean in terms of performance. Drag translates to energy used to cover a certain distance. You're familiar with the concept from your best glide angle, which is also the minimum drag speed for your aircraft. Power is related to energy per time, as opposed to energy per distance. And you're very familiar with it in terms of gallons per hour. Gallons of gas, of course, is just another store of energy. When you're gliding, you're converting height energy to distance. It's no different when you're converting chemical energy in the form of gasoline into distance. The physics are the same, so the best glide speed also gives you the most air miles per gallon. I should mention that the speeds may not be completely identical because a gliding aircraft has additional drag due to the windmilling propeller. On the power side, you'll know, for instance, that a 180 horsepower engine operating at 75% power, that is, delivering 135 horsepower, will consume a little over 10 gallons per hour. That is true for pretty well any 180 horsepower aircraft at any speed and altitude. Another way we generate power is by letting the aircraft sink. So if you want minimum sink rate in a glide, you operate at minimum power speed, which is lower than minimum drag speed. Glider pilots know all about this. They fly at minimum power speed to reduce sink rate in a thermal, but they accelerate to minimum drag speed when out of the thermal and trying to make maximum distance. Power consumed is drag times speed. So because there is a speed component to power, minimum power occurs at a lower speed than minimum drag. One interesting thing is that if the drag is the same, you get the same miles per gallon, irrespective of speed. So for instance, a truck traveling at 50 miles per hour with a drag of 300 pounds will consume the same fuel per mile as an aircraft traveling at 150 knots with the same total drag. I'd like to talk to you a bit about lift-drag ratio and the glide. Now, we've all heard that the glide angle depends on the lift-drag ratio, but I'd like to show you exactly why that is. And the interesting thing is it's got nothing to do with aerodynamics. It's purely a matter of mechanics. Here we have an airplane gliding along the yellow path, and as we know, lift is perpendicular to the glide path, so it's that green arrow pointing more or less up. Lift is not pointing vertically, but it's pointing more or less up, and added to it vectorially is the drag, which is that orange arrow, which is parallel to the flight path. As we know, drag is parallel to the flight path. The resultant of those two is the upward pointing grey arrow, which is exactly equal to the weight. How do we know that that resultant is absolutely equal to the weight? We know because the aeroplane is in steady flight and is not zooming all over the place or accelerating. So we have two triangles. One is a triangle of forces up at the top there, and one is a triangle of distances flown and sink rate or velocities, whatever choice you make for that triangle. And those two triangles are similar, which means those two angles are the same. The two angles that I show there are the same. So the lift-drag ratio is exactly in the same ratio as the height loss per distance flown or the sink rate per forward velocity. Exactly the same. Notice that weight doesn't enter into it. The weight is irrelevant. So glide angle is completely independent of weight. It depends only on the lift-drag ratio, and therefore it depends only on the geometry of the aircraft. The higher the weight, the faster the optimum speed, but the angle remains the same, and that is why gliders that are flying in strong thermal conditions will fill their wings with water. It allows them to have the same lift drag ratio, in other words the same glide angle, but everything happens at a higher speed. Because the lift drag ratio depends only on the geometry, a clean aeroplane like a Boeing 747 has a much better glide angle than something like a Cessna 150, which is interesting, isn't it? Now let's have a look at the engine. The fuel burn depends on the power setting. If you're getting your power at a higher RPM, as happens with a fixed pitch propeller as altitude increases, then there is in fact a slight increase in fuel consumption because the mechanical efficiency is lower at higher RPM. Gasoline has a high energy density, about 8 horsepower-hours per pound. Unfortunately, the laws of thermodynamics don't allow us to harvest all of that, and we end up with an output of about 2.2 horsepower-hours per pound, or around 0.46 pounds per horsepower-hour consumed. This kind of performance can be achieved quite easily by the sort of low revving, large capacity, simple engines used in aircraft, provided that the engine is lean properly. But it's quite hard to improve much beyond this. For instance, about the pinnacle of aircraft piston engine development was represented by the Wright Cyclone of the 1950s, which had a complicated power recovery turbine that passed about 750 horsepower back to the crankshaft from the exhaust gases. It had a full-time flight engineer looking after it, who had some fairly sophisticated instrumentation. Its fuel consumption was 0.40 pounds per hour, only about 15% better than your aircraft engine. So it's a matter of diminishing returns. It's quite simple to get to the 0.46 pounds per horsepower hour, and quite hard to get beyond that. Incidentally, the best commercial battery delivers about 0.1 horsepower hours per pound, or conversely, you need 10 pounds of battery for each horsepower hour of energy, as compared to less than half a pound of gasoline. So you can see why that electric aircraft is a bit of a challenge. You need 20 times the weight of fuel to provide the same power in an electric aircraft. And of course, once we have power from the engine, we need to turn that into thrust, and for that we need a propeller. The propeller is really just another wing, with the same characteristics as the wing holding the airplane up. For the wing, the amount of downwash depends on the wingspan and the aircraft speed, as you remember from the first lectures on lift. In exactly the same way, the propeller diameter and the forward speed affect the prop wash. Both the downdraft and the prop wash represent lost energy, so we have the same interest in reducing both. When you're running up to full power against your brakes prior to a short takeoff, the prop is producing maximum thrust, but no useful work, so the efficiency is zero. As the aircraft accelerates, the thrust decreases, and the efficiency goes up. Again, there is a point of diminishing returns. It's quite easy to get a maximum propeller efficiency of about 85%, and very hard to go beyond that. Propeller designs are usually optimized to deliver best efficiency at top speed at sea level. That provides about the best compromise in performance. As in the case of a wing, speed reduces prop wash and therefore lost energy, so you can get good efficiency in a fast aircraft with a small prop. Take a look at the relative sizes of the propellers on these two aircraft. If you go fast enough, you can get good efficiency even from a jet, which has a very small diameter. So now let's have a look at a real aircraft. I've chosen the Cirrus SR20 because as a composite aircraft without rivets and with compound curves, it's amongst the most efficient light aircraft. Also, the data in the flight manual is more accurate and coherent than in some, and I use the flight manual to extract the aircraft drag characteristics. Here we have the drag curves for the Cirrus SR20 at a gross weight of 3,000 pounds. The green line is the induced lift-dependent drag. The purple line is parasitic drag, and the orange line is the sum of the two. Induced drag is high at low speed and drops rapidly, so that at cruise speeds of about 140 knots, its influence is small but certainly not negligible. And parasitic drag goes up with velocity squared. The clean stall speed on this aircraft is about 65 knots. So all that very high drag part of the curve on the left hand side is more or less theoretical. Now, minimum drag is always where the induced drag and parasitic drag lines cross, and on this aircraft it happens at about 96 knots. At 96 knots, drag is a minimum at about 220 pounds. The maximum lift drag ratio is 3000 divided by 220, that is 13.6. And that is also what the best glide angle would be if we didn't have a windmilling propeller, which decreases the glide angle to something like 11. As the air miles per gallon is the same if the drag is the same, for this aircraft you can operate at about 70 knots or about 130 knots, and the air miles per gallon will be exactly the same. The fuel flow won't be the same. You'll be using much more power at 130 knots than at 70 knots, and therefore the fuel flow will be much higher. How much higher? 130 divided by 70, or about 85% higher. The higher fuel flow will be matched by the increase in speed, yielding the same air miles per gallon. Let's add propeller thrust to this drag curve. Because power is thrust times speed, the maximum power thrust drops off almost in a straight line as speed increases. At low speeds there is tremendous thrust, and until the aircraft is airborne there is no induced drag, so propellers aircraft accelerate well and have short takeoff distances. But in fact, because piston aircraft operate more in terms of constant power than constant thrust, it's more instructive to look at the performance in terms of power. Power, as you remember, is drag or thrust times the speed. Let's have a look at the Cirrus's power curve at sea level and 3,000 pounds gross. The power curve looks a lot like the drag curve for the minimum, but notice that the minimum power speed is quite a bit less than the minimum drag speed of 96 knots. In fact, it is about 74 knots. Maximum engine horsepower is 200 horsepower. Maximum thrust horsepower is about 170 horsepower because about 30 horsepower is lost in the propeller prop wash and prop wash losses. The 170 horsepower gives a maximum speed of about 161 knots where the red and green lines cross. Because of the constant speed propeller, engine power is constant with speed, but efficiency isn't. As the speed decreases with the engine operating at full power, more power is lost in the prop wash, reducing efficiency and therefore thrust horsepower. So the maximum available thrust horsepower curve drops as the speed drops. If the aircraft needs 60 horsepower to fly and the engine propeller combination is producing 140 horsepower, what is happening to the extra 80 horsepower? Where is it going? It is absorbed by adding potential energy to the aircraft, which means that the aircraft climbs. Best climb rate happens where you have the most excess horsepower, that is, where the gap between power required and maximum thrust horsepower available is the greatest. That condition occurs at around 90 knots, where I've got the green arrow. But in fact, the curves are roughly parallel in that region, so the climb rate does not decrease much if the speed is increased a bit. Increased speed gives you better engine cooling and in fact better prop efficiency, both positive effects. So generally, where possible, you'll use the cruise climb speed rather than the maximum climb speed. Throttling back at 75% power, the thrust horsepower is about 124 horsepower, yielding a cruising speed of around 142 knots. The minimum power speed corresponding to maximum endurance is about 73 knots. The minimum power required to keep this aircraft aloft is about 52 horsepower. If the engine quits and you fly at 73 knots, a 3,000 pound aircraft generates 52 horsepower when it has a sink rate of around 10 foot per second, or 600 foot per minute. So what speed should you fly when there's an engine failure? In your training, you were told to trim for best glide angle, which for this aircraft is trimmed for 96 knots. At 96 knots, the power required is about 65 horsepower, which translates to a sink rate of around 800 foot per minute. Minimum power speed of 73 knots gives you a slower sink rate of 600 foot per minute. I would suggest that when your engine quits, for the first little while at least, you don't even know where you're going or where you want to land, so it's important to sink as slowly as possible so you have time to think. Moreover, if you trim for 73 knots and plan your emergency glide and touchdown based on that, you have a little performance reserve in hand. If you find that you're going to be a bit short, accelerating to 96 knots gives you a better glide angle, particularly into the wind. If you're already at your best glide and you're coming short, then you really are out of options. Except, of course, in the Cirrus, where you probably would pull the chute rather than risking any kind of forced landing. But I suppose that the training based on best glide has a lot to do with keeping a panicky pilot away from the stall speed. Best power speed is always uncomfortably close to stall speed. But for this aeroplane, let's say we're at 600 foot on takeoff and the engine quits, too low for CAPS deployment. Can we make the impossible turn and land on the airfield? If we fly at 73 knots, as I said, we have about 1 minute to touchdown. A rate 1 turn will get us through 180 degrees in 1 minute, but a rate 1 turn at 73 knots is a very flat turn indeed. A 30-degree bank turn will get us around in 24 seconds, but at a higher sink rate, 720 foot per minute. But if we have nerves of steel and can maintain that 73 knots in a balanced turn at about 30 degrees, we will be able to make it with enough time to straighten out and land properly. The big dangers are in not maintaining speed in the turn, or crossing the controls, or ruddering into the turn. Perhaps one wants to do the turn with feet flat on the floor. Whether or not this is a good idea is another thing. It's probably safer just to land straight ahead as you have been taught. The power performance of aircraft has a subtle effect in slow flight. Say you're flying VFR and the weather has closed in, driving you to a low altitude. Perhaps visibility is poor and maybe you're a bit distracted looking for an airfield, so you're flying slowly. You're trying to maintain altitude, but you notice that you have sunk a little. Instinctively you raise the nose. If, say, you're flying at 85 knots, initially you'll get a little altitude fillip as you slow down and the excess speed is converted to height. After that, because you're flying now at say 75 knots, where the power requirement of the aircraft is lower and the engine output is still about the same, you will get a slow climb, which is what you want. But say you were flying at 75 knots, what happens? The aircraft slows to say 68 knots, giving you the same comforting initial fillip as it slows down, but then because you are now behind the power curve, it actually starts to slowly sink. If you're busy and distracted enough, maybe you try raising the nose more, and the aircraft sinks more, and you're very close to stalling speed. this is the way accidents happen. Let's see what happens at altitude. In terms of drag, not much. The drag remains the same except that the curve moves to the right. As you see, the yellow curve is the drag of the Cirrus at 8,000 feet. The aircraft flies on calibrated airspeed, so as you gain altitude, the same CAS gives you the same drag, but a higher true airspeed. Minimum drag is the same, but minimum drag speed at 8,000 feet is now about 110 knots true airspeed. Your ASI will still read 96 knots though. At 8,000 feet, your airspeed indicator may read 128 knots, but the true airspeed increases to 144 knots. Again, because the drag is the same at 144 knots at 8,000 feet as at sea level at 128 knots, the air miles per gallon is exactly the same in these conditions. So you get a boost in speed from 128 knots to 144 knots for nothing except the energy and time required to climb to 8,000 foot. And much of that climb energy can be recovered on the descent. Let's take a look at what happens to power at altitude. Note that the power required curve doesn't just move to the right, it also moves up. At 8,000 feet, minimum power is at about 62 horsepower, and it occurs at around 83 knots. At the same time, engine output declines. The maximum available from the engine is around 75% power at 8,000 feet, yielding thrust horsepower of about 125 horsepower. At sea level, that 75 horsepower resulted in a speed of about 143 knots, but at altitude it yields a speed of 153 knots. You can see the attraction of turbocharging. If we could maintain sea level power at 8,000 feet, we could get a top speed of over 175 knots. Just for fun, let's imagine the Cirrus as a jet. First, let's envisage a jet that would give us the same top speed as the 200 horsepower piston engine. That engine would be delivering about 350 pounds of thrust to give a top speed of 162 knots at sea level. Now a jet is more or less a constant thrust device, so that same 350 pounds would be all that was available throughout the flight envelope. There is little excess thrust available at any speed. This airplane would be a real concrete eater. Takeoffs would be very long. Climb performance would be terrible. So the characteristics of a jet force us to provide an engine with at least 500 pounds of thrust, which would give us a sea level maximum speed of 200 knots. This would give us a reasonable takeoff and climb as well. Now jets deliver about a pound of thrust per pound of fuel used per hour. That being so, it's obviously more economical to use those pounds of thrust at higher speeds. The natural way to do this is to fly this aircraft at high altitudes. If we could get up to 40,000 feet, that 200 knots calibrated airspeed would increase to 400 knots true airspeed with no additional fuel burn per hour, and double the air miles per gallon. So the nature of jets being constant thrust devices drives us to higher altitudes and higher speeds. We'd want to reduce drag as much as possible, so those wheels would have to retract. We would be flying way above 10,000 feet, so the aircraft would need to be pressurized. The whole aircraft gets much more complicated and expensive. Now let's have a look at the performance of two nominally similar aircraft, our familiar Cirrus and the Piper Archer III. The Cirrus is a modern composite with compound curves. It is rivetless and has a cast-ring nose wheel and an optimized exhaust. The Archer is a venerable 30-plus year design, all aluminum, conventional riveted construction, with lots of things sticking out into the airstream. The blue line is the Cirrus's drag curve, which you've seen before, and the orange line is that of the Archer. Note that at all useful speeds the drag of the Cirrus is below that of the Archer. The Archer's minimum drag is higher than the Cirrus's, and the Cirrus is flying at about 127 knots before it has the same drag as the minimum drag of the Archer, which occurs at about 73 knots. Minimum drag for the Cirrus is at 96 knots and is significantly lower than that of the Archer. The drag disparity is quite marked. It is due to the high aspect ratio wing on the Cirrus, smoother surfaces, the absence of the trailing arm steering strut on the nose wheel, absence of gaps and holes on the Cirrus, and general attention to detail. Note you can still get the same air miles per gallon on the Archer as the Cirrus. You just have to fly slower. So for instance, the Cirrus at 143 knots and the Archer at 115 knots have the same drag and therefore they have the same air miles per gallon. Finally, I just want to talk a little about overall aerodynamic efficiency. Total efficiency is proportional to cruise lift drag ratio and the engine thrust efficiency in terms of thrust horsepower per pound of fuel per hour. It's a measure of ton air miles per gallon. Now, the later piston aircraft, like the Lockheed Constellation and the DC-7, had lift drag ratios of about 16 and fuel consumptions of about 2.1 thrust horsepower hours per pound, for a product of the two of about 34. The early jets came nowhere near those numbers, but of course they were much faster, and that was what counted. Even in the 1970s, the Boeing 747 that came in could not match that efficiency. It's only in the 2000s that improvements in aerodynamics, and particularly in terms of engine efficiency, that have allowed aircraft like the Boeing 777 to beat the prop liners in ton air miles per gallon. The really interesting entry in the table above is Concorde. Concorde had a low cruise lift drag ratio of only about 7 due to supersonic drag. But the high speed creates lots of horsepower per pound of thrust, leading to high engine efficiency, almost making up for the high drag. This kind of back-of-the-envelope calculation seems to indicate that the Concorde should have been almost as economic as the 747. But the sad fact is that many effects kept the aircraft operating well away from its optimum profile most of the time, and that, coupled with high purchase and operating costs, doomed the project from the beginning. This concludes the lecture on performance. The next lecture will be on stability and control.